The FPro Bus is our custom system bus that we're utilizing for our whole subsystem in here. So let's see what's inside it and a little bit about its timing. So again, it's just a system bus, so we're going to categorize its signals or its wires into 3 different categories where we'll have the data, the address, and the control. So in the data, what we have is we have the FP stands for FPro, and we have read data and we have write data in here. So these are the 2 bunch of wires in here. Each one of them in here is about 32-bit. It's actually exactly 32-bit, and the reason why is because we're using the microblaze or any microprocessor that we want to utilize, and that particular microprocessor has to be 32-bit. This is one of the constrictions that we have. And you're going to see in here that I'm actually utilizing that this actually goes from slave to master, and this is the only signal that actually comes from the I/O cores, or it's only from the I/O cores. We don't have memory in our subsystems. We have registers within the I/O cores, not necessarily a memory, and this is the only one that actually comes from that particular register in the I/O to the master, which is actually the processor. The rest of the signal, all of them, you'll see that it's actually coming or initiated from the master, which is the processor, to the slave, which is one of the I/O cores or one of the subsystems within the video subsystem. This FPro bus again is connected to both subsystems, the MMIO and the video subsystem. Next here we'll see that we have an FP, which stands for FPro, and this is the address one. And the address, again, the processor specifies the register and the module or the I/O core it wants to communicate with by placing the address in here. And what we have in the FPro, we do have about 21 bits. Actually, it's exactly 21 bits, and these 21 bits are word addresses, basically. They are not bit address. So there's a couple of other bits if you want the byte address. However, we will deal with our subsystems as if they were systems that only have 32-bit rows or addresses. However, we know that each one of them is conceptually organized in 4 different rows because our memory is aligned. So these particular 21 bits will allow us to specify 2 to the power 21 locations or number of rows. Of course, we're not going to be utilizing all of them. Some of them will be empty, but it allows us to do this, and it's not too much for our microcontroller. Okay, next we go to the control signals. We have 4 of them, and they're pretty simple. All of them are exactly 1 bit. So the first one here is read, and the second one is write. They're associated with when the processor wants to read something from the I/O core, and the other one is when it wants to write something into the I/O core registers. And remember, reading and writing goes into the register of the I/O core. And the last 2 signals in here are actually control signals that tell me which subsystem you want to communicate with. Is it the MMIO chip select or the video chip select? So it just basically, if it's 1, that means the MMIO is the one that you want to communicate with, or if the video chip select is actually the one that is 1, this is what you want to communicate with. And generally speaking, you will see that one of them will be 1, the other one will be 0 for sure, because you just can't communicate with 1 at a time. So we now move to the FPro bus timing. We are restricting our bus operations, all read and write operations, to be synchronous. They're synchronized with a clock, and they must be completed within 1 single clock cycle. This timing diagram here relates to only the FPro bus system, the bus that we're actually utilizing with our own custom built subsystems. It's not the one that is coming from the processor. So in here, I'm showing you some sort of a timing diagram, and I'm going to show you an example of a write and a read. So let's start with the write, which is actually here on the left side. So the processor wants to write to one of the registers in the I/O cores. So what the processor does, it does the following. At exactly T1, this is because it's synchronous, so it has to be synchronized with the clock. So at T1, the bridge, remember, is translating what the processors want. So there are some delays because inside the bridge or the signals coming out of the processor or inside the bridge, they're actually registered. So there's a little bit of a delay in here. So what the processor does, it does the following. It actually places what it wants to write into the I/O core. It also, or which of the I/O cores it wants to write to. This is the address. Okay, so it specifies the address that it wants to communicate with. It also specifies what it wants to write on that particular I/O core. And after it's done that, it actually goes in here and says, well, that particular core is within the MMIO subsystem. So I'm gonna raise the chip select for the MMIO so that I'm not communicating with the video subsystem. And then it raises the signal that basically instruct the MMIO subsystem and the cores and everything to actually be written to, which is the right signal. And as you might see in here, there's a little bit of a difference between T1 and T2. And the reason why is because there is a little bit of a delay between the bridge translating the commands and actually the commands arriving at their destinations. And the reason why is because we have registers. And the registers have a clock to queue delay. Okay, so the difference between T1 and T2 captures that clock to queue delays for all the registers. And at this particular moment, you will see that at T3, there are some decoding. So if you're writing, we will see shortly that if you are writing, that means you are decoding. So there are some combinational circuits in here that is actually taking that address and decoding it. And it takes some time for the decoder because it's a combinational circuit. It takes some time for all the decoders and everything to be activated and for the signals to arrive to their destination registers, to the final actual register that we want to write into. And that happens exactly at T3. So at T3, everything is ready. So the register we want to communicate with has the data we want to communicate with. Of course, the address has been basically decoded to activate that particular register. And because we're dealing with synchronous system and exactly we're restricting ourselves to exactly one clock cycle, the next active edge of the clock, which is here T4, that particular register we want to communicate with samples the right data and writes it into it. So what you need to take from here is the processor places the data that it wants to write in here, of course with the address that it wants to write to, and that data gets written to that address exactly in one clock cycle. And this is a restriction we're gonna just do to our system because for the sake of simplicity, it just simplifies our designs significantly. Okay, so on the other side, we have the read way. So this is the read timing. It's very, very similar to the write. Now, what the processor does, it places the address it wants to read from, basically the register within the IO core that it wants to read to. And of course, there's nothing on the write data because it's not trying to write anything in here, so we don't have anything in here. And then what it does, it actually tells me I want to communicate with the MMIO subsystem, so raise the chip select for that particular subsystem. I'm not communicating with the video. And it raises the flag that I want to read. And again, that particular difference between T5 and T6 is actually the clock to queue of the registers that are actually holding all this data. It takes some time for the processor, it places it in here. It takes some time for these registers to take and store that value. It stores it in here. And after that, there are actually multiplexing at this particular point, which is up to T7 actually. When you're reading, you're multiplexing, and the reason why you're multiplexing is because you're taking the data, sorry, not the read address, but actually the data that you want. You take it from the core all the way to the processor. So it takes some time to actually route this particular data, the read data, into the processor, and that time is actually a multiplexing time. And at T7, this is when the data is ready. So what's happening in here is the data coming from the IO core got routed all the way through the buses, all the way to the processor at the top, okay? And then at the next clock cycle, the processor samples that particular value and stores it, and at this particular moment in time, it actually read the value of the register for that particular IO core. Again, what you need to take from this particular diagram is the following. The processor places at T5 the address it wants to read from and raises a value or a flag that it needs to read, or the read signal. And in exactly one clock cycle, by T8, it actually reads that particular value. So everything is restricted to one clock cycle, whether it's read or write.